Hi, welcome to the Monday lecture. We missed the Monday lecture because of the public holiday. So this is our opportunity to record the contents of Monday's lecture. So what I'm going to do is share the screen and go through the contents that I would cover on Monday and make this video available to you. So let me share the screen. Okay, so let me get my annotation tool. Okay, so the topics are DNS, peer-to-peer video streaming, and CDN and socket programming. So on Monday, I would like to cover P2P and socket programming, and leave DNS and CDN. CDN also uses some DNS services for Thursday face-to-face in-person lecture. So let's start with P2P. Let's go straight to P2P. I'm skipping DNS, but we'll cover DNS on Thursday. Okay. So we have covered client-server paradigm in email, in HTTP in the last lecture. But today we are going to look at peer-to-peer, which is a different kind of system for providing services in the internet. As you can see here, with the client, with the peer-to-peer, the clients can directly communicate with each other without going through the server. So the main benefit of that is this scalability, right? So I will show you shortly the motivation for peer-to-peer. It provides a scalable solution for the internet so that you don't get bogged down with the server capacity. So if you're looking for examples, then you can see that we have examples such as BitTorrent for sharing files, video files or anything. For video streaming, we have CanCan, we have Skype. This is also peer-to-peer. We have Bitcoin for cryptocurrency. So there's quite a few examples for peer-to-peer. So one thing I want to mention here, in case you are confused, is that writing the client side of the program and the server side of the program doesn't end here in peer-to-peer. Although this is peer-to-peer, you still need to write the client and write the server program. So let me show you what I mean. So this is your peer, this is your peer, right? So this is your peer 1, and this is your peer 2, or if you like, this is your client 1, and this is client 2, and they want to directly communicate with each other without using the dedicated server, for example. But what you have to do, you have to write both the client and the server. So this is client. So that's the client program that you have to write, and you have to write the server program. So in effect, what you are doing is you are making every client a server as well. And this client will also have to do the same thing. It has to run the client side. So if you're running BitTorrent, for example, you have to implement the BitTorrent client, and you have to implement the BitTorrent server program. So you still are kind of doing the client server programming, if you like. So this client, when it's downloading something from this client program will talk to this server program. And this client program, once it wants to download something from this client, it will talk to the server program of this client. So this is interesting, and sometimes some students confuse with the client-server programming versus server infrastructure. So we do not have the separate server infrastructure here, but that doesn't mean that you do not have to have the client and server programming. So client-server programming is fundamental to any computer networking, whether it's peer-to-peer or typical client-server architecture. So that's the point I wanted to make here. Okay, so the next thing is the motivation. So why we are doing peer-to-peer? And as I said, that peer-to-peer huge motivation comes from the scalability. So let me explain that. Okay, so to explain that, we assume a typical infrastructure in the internet where you have a server, right? And you have many clients, right? And this is US is the server upload capacity, and UI is the client upload capacity to the internet, right? So it's the upload bandwidth and it's the download capacity. Usually the server has a good internet connection because it has to serve many clients. So US is typically much higher than UI. So typically what we have is significantly greater than UI. Okay, so what we want to find out is why peer-to-peer can scale better than the client server. Okay, so we are going to do some numeric calculation. It's formula, if you like, an equation in mathematical modeling with a file size of F. Okay, so here we have a file of F bits. It can be a video file, it can be an image, it can be a text file. So it has F bits, right? And this server wants to distribute this file to all of these clients. It may be a update patch, software update, or it may be another operating system update. And all this server needs to distribute this F bits to all of these clients. So first we do client server, right? And what you can see is that this server will have to upload n times F over US. So F over US is the time it takes to upload the file to the internet once, right? But there are n clients here, so it will take n times F over US, right? But if you look at the download speed of the clients, we consider the slowest client, and for the slowest client, this is the time it takes to download a file. And then you will see that the time it takes for the distribution to be completed for all the n clients is the maximum of this server upload of all the n copies of the file, and the slowest client downloading from the internet, whichever is greater, is the time it takes to complete the distribution of the n copies of this file to all the clients. Now, when n is very large, right? Typically, you can have hundreds of thousands of clients who needs to download this file from the server. So if n is large, then you see that the distribution time in the client server model is dominated by this one when n is large, right? And if this is the case, then you can see that it increases linearly with n. So if you increase the number of clients by 1,000-fold, then the distribution time will also increase by 1,000-fold. So it doesn't scale very well. So that's why we go to peer-to-peer. So now let's look at the same context, but this time we have peer-to-peer. What is peer-to-peer? So peer-to-peer means these n clients can actually download bits of this file from each other. Right. So once a file has been uploaded by the server to the internet, or a client receives some parts of the file, it can actually share parts of that file with the other clients directly between them without going to the server, right? So the server does not really need to upload more than once, right? So one copy, as we know, it takes F/US, and the slowest client, as we know, F/dmin. So we have the maximum of F/US, F/dmin, but this is interesting. So here what you see, we call this aggregated. This is called the aggregated capacity for uploading to the internet. So now you see that it's not just the server which is uploading the content to the internet, it's the clients who are also uploading to the internet the parts of the file, because other clients are requesting that part from other clients. As a result, what's happening is you have an aggregated upload capacity, which is the server capacity. This is the server capacity. And this is the aggregate capacity of all the clients for sharing the file with the other clients. As a result, the aggregate upload capacity is US plus the summation of all the clients' capacity. So this is much bigger. And as a result, this entity here is much smaller than the previous one here. Here it was only the capacity of the server, but now you have the capacity of all the clients. As a result, you will see that the distribution type in P2P will be much smaller as we increase n, because if you increase n, then you are also increasing this capacity here. So you are increasing the numerator and you are also increasing the denominator here. And as a result, it doesn't grow linearly, but rather it stabilizes very quickly, as you can see in this example. So here we take F/U as 1 hour, and we take the server upload capacity 10 times the client capacity. And as we increase the number of clients, as you can see that in client server, it increases linearly, but in P2P, the distribution time of the content to all the clients stabilizes, and it doesn't grow significantly as we scale the network. So this is the fundamental motivation for P2P. So you can quickly distribute some content throughout the internet, even if you have millions of clients requesting that content. So we are going to look at some practical examples. So there are many examples, as we have discussed. So BitTorrent is one of them, right? So BitTorrent works for any file, and it divides the file into 256 kilobyte chunks, right? So it means that the minimum amount of content of that file that the clients can exchange with each other is restricted by 256 kilobyte, right? And how does it work? So you do not have a server to serve the files to the clients one by one, but instead you have a different kind of infrastructure, which is called a tracker. So tracker means that the clients who are participating in this BitTorrent needs to register with the tracker for a particular file. So at this point, there are many clients, as you can see, and if a new client comes in, let's say that Alice is a new client, it first goes to the tracker saying that I'm interested in this file, who are participating in distributing this file. And this tracker would give a list to Alice, and Alice can contact some of them and create some TCP connections. So these are TCP connections. So these are TCP, right? All of them are TCP. TCP, TCP, TCP. So at this point in this picture, you can see that Alice has 1, 2, and 3 TCP connections to 3 different clients to exchange parts of this file, so she can complete the download of the entire file. So in the beginning, right, Alice will have no chunks, right? It has nothing, right? But it will accumulate over time because it's contacting the other clients and trying to download different chunks, the missing chunks of the file from different clients, right? So when you are downloading, right, you also have to upload, right? Because other clients, once you establish a TCP connection with another client, you just don't download. The other clients might ask some chunks that they are missing from you. So you have to upload as well. So you're downloading and you are uploading as well. So that's why you have to implement both the client and the server programs within your machine, right? However, you can decide with which peer you can upload, right? So this is your decision because this machine belongs to you and all decisions belong to you. This is not controlled by a central server, but is controlled by the individual peers. We will see later that it creates some competition, and there are some theories behind this kind of sharing. So what happens once you get all of the chunks of the file, you are done. So you can leave this torrent, this community, or you can stay to serve the other people. So usually, people are selfish. So when you are done your file transfer, you'd switch off and you don't want to serve anyone else. But it doesn't matter. If it's a large number, there are many clients, then you can find some other clients to download from. Okay. So in this slide, we are going to talk about 2 things. One is rarest first. What is rarest first? So rarest first is the rule used by the client or by the peer to decide which chunks you want to download next. Right, so you have a large file and the file is broken down into many chunks, 256 kilobyte chunks. So you have some of them, but you have lots of them are missing, right? So you contact your peers, which chunks do you have? So it gives you a list. Then you contact this peer, it gives you a list that I have these chunks. You contact another peer and it says, I have these chunks. So now you can see, oh, I can download this chunk from this client, I can download this chunk from that client, and now I can download these chunks from that client. But how do you decide which chunk to download next? So that decision is made by rarest first. It says that you compare the chunks from different peers and you try to download the one that is held by least number of peers. So let me write it down. So rarest means the chunk that is held by the minimum number of peers. So it means it's the rarest one. So you want to download it quickly before that peer vanishes, right? And if the other chunks are abundantly available and held by many peers, then you can download them later, because even if one of the peers vanishes, then you can download it from other peers. So that's the rationale behind rarest first. The second concept that we will discuss is tit for tat. So you need to make a decision who you want to serve, right? So you have to send the chunks to the other clients or other peers, but this is your decision, right? So the way this is done is you select 4 top ranked peers that you want to serve first, and you don't want to serve anyone else. So how do you select that? So this is tit for tat. This is from the game theory. It says that if someone is giving me good service, then I'm going to give them good service. If I'm not getting good service from someone, I'm not going to give them good service, right? This is tit for tat. And this is how it works. So you monitor the downloading performance from different peers. So you request chunks, and if someone responds to you quickly, then you give it a good score. And by giving scores, you can rank all of your peers, and the top 4 peers you are going to serve first. And every 30 seconds, you are going to update this list of 4 top performing peers. You can optimistically unchoke from time to time. What it means is that maybe if you're just working with 4 top performing peers, then maybe you are not exploring some of the peers who could be very kind to you. So the way you do it occasionally, right, you randomly select another peer outside these 4 and see how they perform. For example, you unchoke Bob, and you might find out that Bob is serving you very well. So that then you bring Bob in the top 4, and then Bob will also put you in his top 4 because you are serving Bob well. And this is how it works, the tit for tat, and it evolves and dynamically adopts these lists for the peers. So one thing to note here is that the peer-to-peer is completely distributed. The decisions are made distributedly, independently by different clients based on their observation of the other clients. But this largely works in the internet if there are large number of clients and peers participating in this kind of peer-to-peer networking, which is the case for many successful applications such as Skype and BitTorrent. Okay, so let's finish it off with a quiz. The quiz is saying that the BitTorrent uses tit for tat in each round to do what? A, determine which chunks to download. So do we use tit for tat for download? The answer is no, because tit for tat is not for download, it's for upload. So how about B? Determine from which peers to download chunks, right? So the answer is not right because it's not about download. How about C? Determine to which peers to upload chunks. Yes. So this is the correct answer. And D and E, as you can see, this is obviously not correct because you don't report to the trackers anything because there is no centralized management of who is doing good, who is doing bad. These are all individual observations, and you have to maintain these observations to yourself and make decisions based on that. Right. So we are done with peer-to-peer, and we now want to move to socket programming because this is Monday lecture, and we want to leave the DNS and the CDNs for Thursday. So I'm going to skip again the contents here and moving to socket programming. Okay, so we have already touched on this concept that socket is like a door, and if you're an application programmer, socket is like an interface with the transport layer, right? So once you select the transport layer, you create a socket, and you just send your data to this socket, and the transport layer takes care of it and sends it to the server. Right. What we want to see is the UDP socket. As you see that this is the simplest one. and it doesn't require any connection, so there is no connection set up. So by the way, this is the lecture on socket programming, so there's no actual hands-on programming involved in the lecture. Hands-on programming with socket will be done in the labs, and there are some specific tasks for you in the lab to write the code for UDP and TCP sockets and try them out in the real network. You can choose your language. You can use Python, Java, C, and the snippets of socket programming codes are already given, released in WebCMS. I think it's under week 1, so you can go and download them to start with, and you should be okay to implement them. So UDP is the simplest one, and there's not much to talk about, but I would like to move quickly to TCP to explain how TCP works. So TCP is connection oriented. It means that a client process needs to establish a connection with the TCP server side of the socket, and this is byte based. So a couple of things I want to explain in this picture. TCP is byte based, right? So it means that the client can send the bytes into the socket without worrying about the TCP packet, and the socket will create the TCP packet and send these bytes. The reason is the TCP will number each of these bytes, and because it's a reliable connection, it will try to make sure that every byte has been received correctly. These things will be clearer to you when we explain TCP in subsequent lectures. So that's one thing, is byte based. Another important thing is that TCP is connection oriented. It means that you need to establish the connection first before you can communicate, and this is called handshake, three-way handshake, right? But I'm going to make some changes in this picture. This is from your textbook, but this is not entirely correct in the sense that this three-way handshake actually happens here with the connection socket. So let me explain to you what is a welcoming socket and what is connection socket, why there are two sockets. In UDP, you just have one socket, but in TCP, you have two sockets. Why? Okay, so the way it works, by now you know that the client will be running the client socket code, and the server will be running the server socket code. So this is the server socket code, right? It is running, and when the client knocks on the door, contacts this server socket, then the server socket needs to establish a connection with the client socket so that client socket can continue communicate with the server socket. But there will be many clients, right? So there will be another client, right? And this one will have its own client socket, right? So this is client socket. Then we'll have another client here. And again, the same thing. It will have a socket, and this is its client socket. And hundreds and thousands and millions of these clients sockets in the internet. For example, for popular HTTP server, if this is a popular HTTP server, then it has to handle hundreds and thousands of clients at the same time. So how does it work? If the server socket is busy setting up the connection and serving the clients and maintaining the connection for each client, then it will be overloaded, and the new clients will have to wait in the queue while this server socket is processing the connection setup. So the queue will overflow, and the new clients will be blocked. And that's why it uses concurrency. Okay, so the concept is concurrency. In operating system, right, concurrency, multi-threading, these are the programming language and operating system concepts. Basically, what it means is that you fork another socket. So when this client socket contacts this welcoming socket, it will, so this is called forking, right? It forks off another process in the operating system specifically for this client, and then asks this client to get involved with this particular socket. And there will be no further communication with this original welcoming socket. Even this three-way handshake should have been done with this one. So this will not be busy. But what you will have here, this is the initial. This is the initial contact. So the only communication from the client socket to the original server socket is the initial contact. And as soon as the server socket receives this initial contact from a particular client socket, it will fork off a connection socket for this client. So let's say this is client 1, this is client 2, and this is client 3. So this connection socket is for client 1. When this one communicates, right? Okay, it might look a bit detoured, but this is initial contact. So it's just contacting the server. And as soon as it contacts, then it will create a connection socket here. Right, and this connection socket is the second connection socket, so that it can do the three-way handshake and the connections. So the three-way handshake. Okay, and three-way handshake and the connections, the pipe. Similarly, when this one contacts this one, it will create another server socket for this client, so we'll call it 3, and this one will have a three-way handshake and a pipe after that, right? So yes, there's a lot of drawing on this slide, but the message here is that the server process or the server socket uses concurrency or multi-threading or forking mechanism to immediately create another socket specifically to deal with that particular client. So if there are thousands of clients concurrently communicating with the server socket, then there will be 1,000 connection sockets created, and there will be one welcoming socket. So there is always one welcoming socket plus n client sockets. So this is the, if you like, so total number of sockets, right, in the server equals 1. So this one is the original one. This is always running and waiting for requests from clients to establish a connection. And n is here. So in this particular case, we have 1, 2, 3 clients. And as you can see, this is 1, and then 1, 2, 3, right? So this is your formula, if you like. So these are the main concepts that I wanted to get across to you for the TCP sockets, because TCP sockets are connection oriented, and that's why we have this complicacy and we need the concurrency and multi-threading. So in the labs, when you are getting your hands dirty, then hopefully you will be able to verify these concepts with your codes. So with that, I think there's no need for me to go through the pseudocode because you'll be working with the real code very soon. So just to summarize, I wanted to say that on Monday, we have covered only two concepts, peer-to-peer and socket programming. And for Thursday, in week 3, we are going to look at DNS, which is a very significant concept for the internet. And that's why I wanted to leave it for the in-person lecture so we can have much more interactions with you to help you understand the intricacies of DNS. And we are going to look at CDN, Content Distribution Network, which also depends on DNS to improve or provide scalable service. So with that, I think I can say that we have concluded our lecture on Monday, and this video recording will be made available on WebCMS as a recorded video from Zoom, because I'm using Zoom for recording this. And this recording will not be available in the 360, which is done for the face-to-face. However, I will make an announcement in WebCMS and Ed Forum where to find this Zoom recording. I also wanted to say that I have streamlined the contents a little bit. So I'm going to update the lecture content file for week 3 to have this streamlined content. Anyway, we can discuss all of these things further in our in-person lecture on Thursday. So with that, I would like to say this is the end of Monday lecture, and see you Thursday. Thank you. Bye-bye.